just do this real kind of quickly. Ethanol. I mean, yes. Oh, does it dissolve in water? Fair enough.
Yes, question go ahead.
Look at that, I was even planning ahead. Chloroform.
Yep.
Actually, that was wrong. So we said yes. Chloroform.
Why is there a 6?
It's a CL.
Oh, sorry.
Now that you know it's a CL, I'm not going to draw it nicer again. But yeah, it's a C.
Okay.
Missed with the. Yeah, I understand. I get yelled at for it all the time. What do we think? No. Okay, interesting. Because in this one, what do we have between the carbon and the Cl? Polar covalent bond, which would generate dipole-dipole forces, or dipole-dipole similar to hydrogen bonding. They're just, for all intents and purposes, the same thing, and yet it's not soluble. Why?
Sounds stronger than the hydrogen bonding that's happening in water.
Remember, these aren't perfect boxes that you just check off and that's the end of it. Okay? It's a gradation off of that marking. The dipole force generated between carbon and chlorine is a dipole force, or a dipole-dipole force. It's just a relatively weak dipole-dipole force in comparison to the strong hydrogen bonding force generated from water. Okay? They aren't similar enough to perfectly overlap. Acetone. I'm not drawing out its full Lewis structure. No, I'm not drawing it out, sorry. This is why solubility sucks. Yes, acetone is soluble in water. Interestingly enough, what's the force it has? A dipole-dipole force coming from a polar covalent bond, and yet now it is. Well, why? Why would acetone all of a sudden have a stronger dipole-dipole force than chloroform? I heard it because oxygen is more electronegative than chlorine, so it should generate a larger dipole. Cool, that makes sense. The dipole-dipole force in acetone is probably a little bit stronger than it is for chloroform. That shifts it high enough to become water soluble. And the last one I'm going to draw sideways and in shorthand. Diethyl ether. And yet diethyl ether has what type of bond? Polar covalent and generating a dipole-dipole force. And yet this compound not soluble in water. Okay. Solubility is not a perfect science. It's far from it. These are approximations that we lay over the top of them and hope that it comes out, and then we test it and see how it worked out. Could we theoretically go into some big computer system, punch in a bunch of values, and have it tell us if they were soluble? Absolutely. And after a day worth of calculations, you would find out. Or you could just say, yep, I think it is, test it, yep, I was right, nope, I was wrong, this is why I'm wrong. In a matter of 10 minutes, you have an answer that fully satisfies all of the limits you could ever want that you would get out of a computer in several days worth of calculations. Organic is qualitative based because the qualitative, for some reason, in organic works well enough that we don't need to quantify. We can predict quickly and swiftly enough with the human brain faster than the computer can. Okay? Does that mean we are perfectly correct? Yes. No. It just means that we are correct enough to get an A in whatever class we're working in. Okay?
Does that go, is that the same with like the organic chemists that are making like our prescriptions?
Yep.
Just kind of guessing.
Yep. Very, very educated guessing. Okay. So what can we do with these interactions? We could look at how our different phases dissolve. We've looked at a whole bunch of different examples. We could look at salt dissolving in water, why oil does not, how soap helps oil dissolve. All of that comes back to intermolecular forces and how we can build these dichotomies. Okay? If we push this even further, we look at soap dissolving, we generate something known as micelles. And say, well, none of this is particularly relevant. I'm a biologist. I'm going to look at medicine. I don't care about any of this junk. Super common drug delivery mechanism is now coming in liposomes and micelles. Okay? Liposomes, a slightly larger version of a micelle. It's actually a bilayer. For those of you going into biology and think none of this makes any sense, or relevance, bilayer sheets are found in cell walls. Okay? It's what actually allows us to exist. All back to intermolecular forces and how they stack and interact with each other. Super, super, super important. Okay? Questions? I said cell membranes, didn't I?
You said walls.
Oh, my bad. I meant membranes. Okay. So here's our next fun topic. This is where everybody's going to get lost and everybody's going to hate me. You just kind of have to deal with it. A bond is an example of an electron home. Okay? The electrons exist between those atoms. If we look at atomic structure, we can define within our atomic structure where our protons exist, which is the nucleus, and our electrons exist. The outer shells are orbitals outside the nucleus. So if we're now going to generate a bond between atoms, we're now telling electrons where they can exist, which means we are telling electrons that they are existing in bonding orbitals. So the atomic orbitals that we know and love from Gen Chem now must necessarily apply to organic and how we put these things together. So if we looked at our structure for methane, what do we get? Here's our Lewis structure. What bond angles do we get in methane? Okay. 109.5, because we all did an awesome job with our Vesper models. And we learned that we actually have 109.5 bond degrees between all of these. Everything is perfectly equal. Everything makes sense. So now let's apply atomic theory to it. Our atomic theory, let's look at our center atom, the carbon, because it's most involved in all of this, has as its highest energy electrons a 2s orbital and 3 2p orbitals available to it. What is the bond angle between the px and the s orbital? That one may have been a little bit difficult, so let's switch that up. What is the bond angle between the yp orbital and the zp orbital? Why do we call it x, y, and z p orbitals? They're defined because they are placed on the axes, x, y, and z. I was going to say p. The x-axis is what bond angle away from the y-axis? 90 degrees.
Where's the S then?
What's the bond angle between the s orbital and the p orbital? Infinite or non-existent. We go to either end. We have no bond angle between them because they overlap each other. Okay, remember, we've got an s orbital here. There's our p orbital laying over the top of it. There is no bond angle there or angle between those orbitals. They're on top of each other. Why is this a problem? When we move to a molecule, our electrons exist in orbitals. We already have orbitals. They're atomic orbitals. So when we move to a molecule, the orbitals in our molecule must have come from our atomic orbitals, and yet the bond angles generated from our atomic orbitals do not match the bond angles that we know to be true using Vesper models. What does that mean? Shouldn't have bothered to learn Vesper. That was a waste of time. We got a new system. No, unfortunately that doesn't work. Vesper was true. We saw that to work. We see it experimentally. What does that mean about our atomic theory? It does not match our molecular theory. There is a failing in the system here. There are two approaches to fixing that system. Both of them are sort of hand-washy, at least at the level that we can discuss. One gets into all of the quantum physics and dynamics of orbitals and where electrons exist, and you add and subtract orbitals and do this fancy calculation that is phenomenally neat and cool, but I don't know anything about. That method is known as the linear, nobody? Combination of atomic orbital theory, the Lakow models, Lakow molecular orbital theory. We'll talk a little bit about its basics at a super simple level in a little bit, okay, probably on Wednesday. Okay, the other model is known as hybridization, which is really just a messed up way of making something that is completely magical and giving it a name that makes everybody think it's real science. What we did is we took all the orbitals and said, well, crap, that doesn't work. Let's match them all together and make some new stuff and say it works. Okay? As stupid as the science is behind doing that, it works. It works. We just took all of our atomic orbitals, we just said, you know, it didn't work, let's just put them all together, blah, 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 spit out some new stuff, boom, there it is. This is what I'm saying it does. And what happens? It worked. Amazing. Okay? This is our qualitative model, hybridization. Our quantitative model is the linear combination of atomic orbitals. Okay? We will use kind of a mix of both when we go through and look at molecular orbital theory. So how does this end up working? Okay? So we've got our atomic orbitals for carbon. There's a variety of systems that we can generate. Okay? And thank you for pulling up the slide over there because I couldn't remember what the next thing showed up. If we go through and say, look at methane. How many molecular orbitals do I need for methane? For the carbon in particular? 4. Why do I need 4? There are 4 distinct bonds. So I need 4 molecular orbitals from carbon to generate methane. So what I'm going to do is go back to what I know to exist for carbon, my atomic orbitals, and say, well, how many atomic orbitals do I have?
3.
Careful. 4. There's the 2s and the 3 2p's, which in total gets us 4 orbitals. Well, I need 4 orbitals in my final answer, so what I'm going to do is I'm going to take all 4 of those, I'm going to smash them all together into one giant pot, and then I'm going to make new orbitals. Okay? Those new orbitals, okay, are going to look like this. I'm going to erase that for the moment. Okay? So I have these 4 new orbitals. Yeah, we can't quite get the feeling for where all these things are located. Okay, if we tried to apply this, I did a horrible job. This one should be spun around the other way. This would be kind of our dash, and this one would be our wedge. It's kind of arbitrary, didn't really matter. But those are our 4 new orbitals. What do I want to call those orbitals? Boom, you're born. What does your parents call? What do your parents call you?
Mike, Bill, Jill, and...
Okay. Come up with an arbitrary name. I like this name because it sounds pretty. I'm going to pick this name because I know the kid's going to have a really rough life if I do this. Okay? There's some kind of logic behind that name. We can do the exact same thing with these. Let's call them Bob. Okay? Now everybody has to refer to these orbitals as Bob. How many Bob orbitals do we have? 4. Okay, so we have 4 new orbitals that we've now named as Bob. The scientists that went through and came up with this theory said naming it some random Bob name isn't very sensible. I want to name it based off of what made these orbitals. Well, what things went into the pot to make these orbitals? An s orbital and p orbitals. How many p orbitals? 3 p orbitals. So what I'm going to call each of these orbitals instead of Bob is sp3. All I'm trying to do is reference what atomic orbitals went in to make it. And I had a feeling that was going to happen. So we have our 4 sp3 orbitals. What if we run into a situation where I don't have 4 groups? Let's make it simpler. If we look at the Lewis structure for boron, we end up with this. How many distinct new orbitals do I need? 3. Okay? The bond angle has to be 120, so I can't just say 3 p orbitals. There's 3 p orbitals, 3 orbitals, hey, they all work, perfect, except the bond angle is 90, doesn't match my result. So I need to take 3 orbitals and bring them into this. Okay? If I bring in my p orbitals, I don't get my angle, I have to bring in the s orbital. Why else do I have to bring in the s orbital? This is an odd question. What's that?
You have to fill the s orbital first.
Why do we fill the s orbital first? Say it again. Lowest in energy. We are all about making lower energy objects. We will always hybridize the s orbital because it is the lowest energy orbital. So if I take the s orbital, I've got 1 of the 3 orbitals I need 2 more. So I take 2 p orbitals. Now when I put this together, I'm going to take those remnant pieces out and I'm going to generate my 3 new orbitals. These orbitals I can't call sp3 because I didn't use 3 p orbitals. I only used 2. So I'm going to call them sp2s. Okay. Think back to 130, even 151. We had those fancy laws. Einstein applied some of this. We cannot create or destroy energy. What are orbitals? Energy. So I started with 4 atomic orbitals. Right now I see 3, right? You on the same wavelength for 3? I want to make sure you're... Right? We got 3. 1, 2, 3. I want to make sure we're all on the same page, right? Okay. What happened to that 4th orbital? It's still there. I just erased it. Okay. I have a leftover p orbital. That leftover p orbital is important to my overall understanding of what this molecule can now potentially do. In the case of boron, it only has 6 electrons around it. Those 6 electrons go into my hybrid sp2 orbitals. They're now all filled. What's left over? A p orbital. What's left in that p orbital? Nothing. What could we potentially put into that empty p orbital? 2 electrons. There's the chemistry that's special behind boron on what it can potentially do. And it comes back to its hybridization and how we built this. What if we switch to yet another system where we only now have 2 groups of electrons around an individual atom? Well, if I have 2 groups, I'm still going to need to hybridize. So I'll take my s orbital because lowest in energy, and then I have to take another orbital, 1 p orbital, and I will generate some new orbitals. I will generate 2 new orbitals, and those new orbitals I will name sp because those were the orbitals I used to make it. What will be left over? 2 p orbitals.
What do you do with the leftovers?
What do we do with those leftover orbitals comes into play when we look at the individual bonding that comes out of these structures. Okay? But before we even get there, we have to make sure that we're all on the same page on predicting the hybridization and predicting one last little piece. You'll notice that in drawing all of these images, for every single one of these, I also kept this little energy marker.
And that's just
What was that little energy marker showing? And that's just
the common direction of energy. But it's a way dumbed down version.
so it is giving me an energy, but it's not just saying energy. Because if it's just saying energy, there was no need for me to include that little hash mark. And you'll notice that little hash mark is included in every single one of these.
Well, that just is the. It doesn't go past
SP3
that.
or higher than
What do you mean it doesn't go past that? The sp3s, or my sp orbitals, are all above it. The sp orbital is actually almost exactly flat with it. The sp3 is well above it.
It prefers to be on the upper. No?
The s orbital's underneath that line.
There's more energy in sp3 orbitals than in sp2.
Why are there more energies in an sp3 orbital than in an sp2 than in an sp?
Because there's more.
More p
Nope.
orbitals went into it.
Look back to your atomic theory. Our atomic theory has s orbitals and p orbitals. Is there a difference in energy there?
Yes.
Yeah, the p orbitals are higher in energy than our s orbitals. What happens when I take something of high energy and I average it with something of low energy?
Goes down.
I get somewhere in between. I get a medium energy. When we go all the way up to our sp3s, we are taking all of our high energy species and we are averaging it with one low energy species, which means we will have an average energy that is closer to our p orbitals than to our s orbitals. Okay? When we move through to the sp2 and sp, notice where the energy of our leftover p orbital is located. It is higher in energy than our hybrids. Why? There is no s orbital averaging it in. We didn't change it. It stays the exact same energy. Our s orbitals are the lowest energy, followed by our hybridized orbitals, followed by our p orbital. So when we're looking for reactive electrons, we want to pick our reactive electrons based on their energy. Be it highest in energy, that's going to be where we start.
I was going to ask, so why, like, if you had like a sp2 molecule and it bonds with something, and it brings down the average energy of that last p orbital? Or
It will, everything is going to work towards lowering the energy of your overall system, and that brings in a whole nother can of worms, but we will look at that as we go through this semester. Okay. So, if we were to look at some atomic hybridizations for these, BH3 I just drew out real quickly, so let's skip BH3 and let's move to CO2. If we look at the Lewis structure for CO2, what do we get? Okay. And we could go through and evaluate our hybridization for this. The hybridization for that carbon will end up being sp. Why? There are only two groups of electrons. So I will end up with some hybrid orbital in here. Oops, I should draw in the other direction. And I will have left over two p orbitals.
Just to be clear though, the atomic orbital of BH3, whatever that is what's already drawn. We're drawing.
No.
Okay.
BH3 we drew up on the last examples.
I got you.
That hybridization comes out as sp2. We're not looking at that one. If I went through and did this with oxygen, I'd end up with something similar. But let's just overlay oxygen as just a simple atom. Here comes oxygen coming in. We would overlay on this side, and we've now formed an interaction between those orbitals. Okay? Those orbitals overlap, and we have a bond. If we came in from the other side with another orbital, it would overlap, and we have a bond, which gets me an oxygen on each side with one bond. When we look at the Lewis structure for CO2, how many bonds are there between carbon and oxygen? Two. We have a problem. Our theory only shows one bond to each side. What the F?
then we get to our high bonds. High bonds look like.
What is left over on our carbon?
Two orbitals.
Our two p orbitals on orthogonal axes, meaning perpendicular. So that if I overlaid one of those p orbitals over the top here, it turns out that our oxygen also has p orbitals. As long as those p orbitals are in the same axis, they can now interact. Will they directly overlap with each other? No, because the hybrid orbitals of our oxygen and carbon can't overlap anymore. So we run into this weird system. We've got this purple interaction where we have a direct overlap of orbitals. And what we've got in red is an indirect, it's even hard to call it an overlap, so we'll put quotes on that, overlap of our orbitals. They're at least in the same parallel axis. Okay. Well, the direct overlap is something that we see all the time. We see that with structures like methane. Well, what kinds of bonds do we have in methane? Single bonds. Well, since that is the most common, and I know it shows up in single bonds, I'm going to pick a term that elicits the thought of single we get, there it was, sigma bonds. Okay. So to generate that double bond, one of those is coming from a direct overlap, which is a sigma bond between them. I still need to account for that second bond, but I don't have orbitals that can directly overlap. But I do have these orbitals that are kind of close. I mean, they can see across and say, hey, what's up? Okay. Take it a step further. Not only is there that space where electrons can't exist, this is a fun little tidbit of quantum physics. Electrons can pass through places where they can't exist. So we build a wall where you say you cannot exist on this side of the wall, or you cannot exist in the wall. And yet somehow an electron will jump from one side where it can exist to the other side. Why? Electrons have this amazing ability to somehow tunnel without passing through something. So what ends up happening, as long as those orbitals are in the proper plane, say this is an X, or so I'm going to run with Y, two Y orbitals, the electron can jump from one orbital to the next, which means it is effectively connected via sharing of electrons, which we have defined as a bond. I cannot call it a sigma bond. Why not?
There's no overlap.
The sigma bond is by definition an overlap of those orbitals. Okay? So I need to come up with a new name for it. Well, what orbitals did I use to make this new type of bond? My p orbitals. Since I picked sigma because it sounds like single, that was the other word. Okay. P orbitals, we go back to our Greek alphabet, pi, and we have a pi bond. So to generate the double bond, I have a sigma bond and a pi bond. Those two bonds in conjunction get me my two bonds. There's my multiple bonding. Why did I say we can only move multiple bonds in resonance? Our multiple bonds are electrons found in what orbitals? P orbitals, which happen to be our highest energy electrons. That's why they move in resonance. Okay? After this, or the rest of that chapter, ends up coming down to how can we combine and make larger structures from these. And we'll look at some overlap with molecular orbital theory. It is mind-blowingly cool to be able to do this. That said, it's not all that important, I guess, in the grand scheme of things. Okay? But we will go through and look at it and how that ends up generating our overlaps, and we'll look at a modified version of our linear combination of atomic theory, molecular orbital theory, on Wednesday.